I could send to. Could you just send the email address on the chat? I can send.
Yeah, okay.
Thank you.
One thing, folks, I want to tell, especially the one who is applying for junior and middle position. Now, what I see for junior and middle position, we're expecting only good algorithms understanding. But if it's come after middle position plus to senior engineer, there is the requirements is quite hard, honestly, become more emphasized. If, for example, for junior and middle, we are good with just algorithm questions, but when it comes to the senior engineer, by default, you should be very excellent in the coding. But by default, you should be very excellent in system design and in your experience story. I mean, from the behavioral perspective. That's why while you're in junior and middle position, and while you can do this, there is a very straightforward process. Just practice LeetCode, came and tackle it. That's it. This is the expectation from the junior and middle position. But then higher your position, then more difficult it will be to enter. So
also, I can add that, for example, in my experience, Google look at my years of experience, and anyway, they defined me interview for entry-level position several years ago. And it's just like, wow, but my title already senior engineer. Yeah, they kind of do these things. They don't care. They may put you as postgraduate even if you already have a few years of experience. And maybe it's fair for them because, again, requirements a bit different, levels a bit different. You can find out that from company to company, you have absolutely different experience and expectations for different levels of engineers. And it's normal because that's how it works.
Kind of encouragement and positive notes, folks. Okay, let's get started. So basically, last time we were talking about graphs. We cover some basic knowledge, not basic knowledge. We found we covered the foundation of the graph. What is the graph? How the graph nodes represent? What type of graph exists? We covered that it is DFS and BFS. We covered how to build graph, some terminologies we covered. And from the homework and what we discussed during the class, it was DFS. Today we will start from BFS. Then we will solve one of the also popular question, what is biparate graph? And then we will cover topological sort. Okay, let's get started. So you have a description. So you have matrix infection. You're given a matrix where each cell is either empty, uninfected, or infected. With each passing second, every infected cell, which is marked as a 2, infects its uninfected neighboring cells, which is 1. That are 4 directional adjacent. Determine the number of seconds required for all unaffected cells to become infected. If this is impossible, return -1. So imagine you have this graph here. You have this one at the beginning, initially infected cell. And this is neighbors of this infected cell. Next second, it will be, the graph will look like this. Next 2 seconds, it will infect, it should not affect this one. It will be 1 here, right? Because this one, yes. And then we infect this one, and this one will infect. This one will be 0. And last, there will be this one, which will be infected. 0 we can't infect. And this one will be 0. From the description, is it clear? So we need, the output will be free. If there is it is impossible to infect all the cells, then we will return -1. Okay.
Sorry,
Yep.
I didn't understand in the second, in round 1 after 0, how did it infect in the second, the last row, the second element? Because no, not that one. So we have 0, 2, 2, 0, right?
Second one or second two we are looking?
Second one.
Second one. So we're starting from 1. There is 1 infected, right?
Yeah.
So we're expecting that it will infect neighbors, right? This one. I got it. This is the
Yeah.
typo.
Yeah, that one. Yeah.
Yeah, this typo. It will be infected on the second 2, and on the second 3, we will infect the last one. Thank you. So, yeah. From the description, you can already see that the representation of the graph will come in matrix. And again, we have for directional. So for in the description as a part, it's mentioned that we have for directional adjacent, means we will infect 4 neighbors. It is not a directional. By diagonal, we are not infected anyone. So let's begin tackling this problem by considering a simple case where the initial matrix contains only one infected cell, like we have in our example. Again, the representation given us in the matrix, but we can see that it is actually a graph. The graph will be looks like this. So this is clear, right? We discussed it last time. If there is someone who wasn't a part, just feel free to ask questions. Okay. After the first second, again, the adjacent unaffected neighbors of the first. So basically, I just again covering the what we discussed just during the description. So after each second, we will infect our neighbors. Then it will be 2, 2, 2. And on the third step, it will be distance free. Why distance, you will understand now. As we can see, the outwards expansion of the initial infected cell is similar to how level order traverse work in the tree. Is it understandable what is the level traverse from the tree?
No, can't understand that.
But in the tree we were covering, there is devise and bfs.
Yeah.
And when it comes to devise, you usually traverse left, then you come back to the right. That's how you traverse. But when you're using bfs, you actually traverse level by level tree, right?
Yeah.
So this is the similar traversing. You're starting from, this is 0 level. Next, you coming all the neighbors on next level. Only neighbors. It is not devise. If it would be devise, then infection will go all the way like this, right? Or all the way like this. But in this case, we can observe that infection is happen on the level. This is first level. This is second level. This will be our third level, and this will be our fourth level. So just observing this, because we also covered that graph, and tree is just the special type of graph. By intuition, when we notice that infection comes with the level order, we just can click that this kind of task can be solved with bfs, not with devise. The difference between devise and bfs, that in devise we're usually using recursion or stack, and for bfs we're using queue. This is the idea. So basically, once you click with the idea and you saw the graph, you saw the level, and you think that it should be solved with bfs. And we discussed how the bfs code looks like for the graph. It looks the same like for tree. There is also using queue. The difference only that we are tracking visited nodes. Okay. Level modifier version BFS. Matrix with multiple why modified version of BFS. Do you remember when we were in this example? Here we have just BFS. This is the classic one. But modified level is the one where we were taking the queue size in order to track actual level, in order to process nodes in the level. So meaning when there is modified version of BFS, we will use this modified version where we actually will track all the nodes on the level. Meaning that we will use queue. First we will put this level, then in queue we will put these nodes, we will process them, and then we will process this one. That's how we will count. Means again, seconds is actual level on the graph, and this will be our output. By how many levels we need to process. It will make clear now. So matrix with multiple. Consider the following example. 1 second. Meaning there are multiple cells at level 0. There is some. So while I will go forward, we just cover case where we have one infected cell and how we are going to solve it. Is it clear why we decided to use BFS with modified version and why it is level order? Okay, cool. Now, now let's discuss how we will solve the same task, matrix with multiple infected cell. Meaning, so for example, you have matrix representation where we have multiple infected cell. Meaning, so for example, it's also could be represented in this matrix. We actually having two graphs. And each of graph, one graph has two infected cell, and another graph has one infected cell. Meaning that infection will start not from only one cell, but it will start from each of these cells. Yes, so consider example. We have these graphs initially. On the second one, there will be start infection from this cell, and from this cell. It will go in parallel, means we will infect in parallel more cells. All the cells which has infected neighbors will be infected. This is the idea. So, is it clear? The task could be like this. And now I will explain how we are going to solve this task when there is more than one infected cell. So, to handle this, we use a pattern known as multiple source BFS. Instead of adding just one cell to the queue, before performing a level order traverse, we add every initial infected cell to the queue. This way, the traverse starts with all initial infected cell as level 0, allowing the infections process to begin simultaneously from multiple starting points. It will be like if someone very familiar with how the concurrency is working. So basically, we are working not with one thread. We will work with different threads, and all of them will do in parallel the infections. In order to handle this case, we're usually using multi-source BFS. Meaning we have queue, but usually what we saw so far on the tree example, we put just one cell. But in this case, we put all of these cells in the queue here. They will, and we will start process all of them on this level. means this one and this one will be first level 0. Then once we will process them, we will process, we again will add all the infected cells on the level 1. So from the perspective with 1 or 2 cell, it doesn't make any difference. The second is the iteration of the process will be the same like for 1 cell. But the idea is that from the initial step, there will be not 1 cell, but because we have multiple infected cell on the first initial state of the queue, there will be all these cells. Let's just take a look at the code. Maybe it will be become a little bit clear. So we will create queue as usual. Initially, instead of putting just one, if it would be just one, we usually do like this, like queue add new cell. But this is not the case here. We're doing multiple sorts of queue, and that's where we will traverse all the matrix. We will see if the matrix is infected, and we will all this infected matrix from the initial step will add to the queue. And next, it will be look the same. This is our modified queue. What we are doing here, all the same, we are processing queue. We are taking a snapshot of the level. It is our size of the how many infected cells in, and then we level by level just popping them and processing. Is it clear? Okay. So this is something which is you should remember. It will it is applied to multiples graph problem. I believe we will cover topological sort, and in topological sort, you also will use multiple source BFS. Just to remember that this pattern. Okay, now we can be task. So our graph can have this representation. In this representation, so for example, yes, we can infect 1 and 1 neighbors, but this one won't be infected. Means in this case, we should return output as -1, because the whole representation of the graph won't be infected, because we have isolated graph here. How handle it? So one way to account for this is to search. So for example, when you one way will be once you process it. So for example, at the end, you can just iterate again level by level and check if there is at least one cell left with 1, then you will return just -1. Or you can go with optimal solution when you're building your multiple source queue. You can just remember how many ones you have seen, because anyway, you're just iterating. So this is pure optimization. You're walking through the matrix, and on the initial step, you're putting all infected cells in the queue, and meanwhile, you're also counting how many ones. Why we need to do this? Because before returning the answer, we need return or seconds or -1 if there is something which is still uninfected. But as I mentioned, you can do this, you can skip counting once here on this step and just traverse the whole matrix afterwards, because you will modify your matrix during the traversing. Is it clear what we discussed? Okay, now let's walk through the code. So representation is matrix. we are using BFS. We discussed why we're using BFS, because infection is happening on the levels. Our direction two-dimensional array. You remember, right, folks, why we're using this from the previous class. If someone wasn't here, I can quickly cover it. Okay. Now, so initially we built queue. I will remove this one. Initially, we built queue. We built our two-dimensional direction array in order to traverse, because representation in matrix. So we need to define neighbors on the up, left, and right, and down. So now, first step will be to traverse the whole matrix. We also discussed last time how we're traversing the matrix. We're checking each cell if it's ones. We just count how many ones we saw. And we're building our multi-source queue. We're adding cells which is already infected. Next, we will go with BFS over the graph. So modified BFS, we discussed during the tree that that's how we measure the level. Because once we will process level here, it means that it is first second. So actually, maybe it will be more readable if I will put the second not at the top. So for example, once we will process first level, it should be here. We will increment our seconds. Means 1 second is passed. This how we are counting neighbors. We're creating the cell of the neighbor. We discussed it last time. Also, feel free just to ask if you don't remember. So we are checking if it's within bounds. We also discussed it last time that because we're working with matrix, we're building the cell dimensions, and it could go beyond the matrix. So we're just checking if we're still in bounds of the matrix. And also, we're interested only in ones. We are not interested in zero, because in zero it means empty. So we are checking our neighbor in bound, and if our neighbor is actually one. Once it's one, we are confirm it. We mark it as a two. We mark it as a two because that's how we tracked our visited matrix. The same things we did for islands last time when we were counting islands. Instead of introducing the data structure where we're tracking visited cells, we were just modifying them. So the same things we're doing here. We're just modifying because it is infected. Also because this is for our optimization. We are decreasing the ones numbers, means this cell was infected, and we're putting it in the queue in order to process it on the next level. Here we're just checking neighbors. If it satisfies our condition, we are putting in the queue. Once we process it in the level, that's how we process it in the level, we increment our second. And we're starting again to process next level. Is it clear? So it's actually a very cool one task, which is I like. It took me some time to understand multiple source BFS. I will just show you here. It is calling rotating origins. So it sounds almost the same, but in this case, you have infected orange. It's also like matrix. On each minute, it will be infected. Yeah. So basically, you have rotating on orange for your homework. Okay, folks. If it's clear, I can move to the next one. So biparate graph validation. Given undirected graph, determine if it's biparated. A graph is biparated if nodes can be colored in one of two colors, so that no two adjacent nodes are the same color. The input is represented as an adjacent list, where graph I is a list of all node adjacents to the node. 1 second, we'll check. Good, yeah. So here we are dealing with adjacent graph. So difference between the adjacent graph, it is that we are dealing with neighbors and not with the cells here. It is the list. Do you remember, folks, right? Okay, cool. So list of node. So in this case, given undirected graph, undirected we also remember, right? That 0, 1 is connected and 1 to 0 is also connected. The idea is that we need to validate if we can color this graph the way that, so for example, adjacent nodes are in different colors. So for example, 0 and the neighbors are in different colors. And for 1 is also in different colors. That's how that's what is biparated graph. So yeah, we can usually rearrange nodes to the following graph to demonstrate this. So this is the biparated graph. I believe it's probably something is using in like a real world with DNA or something. Is it clear what is the biparated graph? Let's now take a look who is not biparated graph. In this case, it is not biparated graph because 3 is adjusted to the 2 and 2 has the similar color. In this case, it's not biparated graph and we can't represent it in biparated way because it is connected here. And if here we can divide it on the set, this will be set 1 and this will be the set 2 with different colors. But in this case, we can't arrange it in biparated view. Okay, if from the description is clear, let's think how let's tackle it. So determine if graph is biparated, we can use graph coloring. We attempt to color one set of nodes with one color and the other set of nodes with another color, while ensuring no adjacent nodes share the same color. So usually, yes, you're given just empty graph. To identify if it's biparated, we usually color them. Orange, vice versa. Most traversal algorithm allow us to color this way, but notice 4 is to be, yeah. So what is written here that you can actually, so you given graph, everything what you need to do in order to define if it's biparated or not biparated graph. You just need to color it. Means you just need to traverse. Meaning there is no strict traverse way, which is you have to use as a devise or bfs, like it was before. In before we saw it clear that this task required bfs traversing because it's level 1. In this case, you can travel in any way, but like devise, it's preferable here because it will be cleaner than having devise. That's why we will solve it with devise. Now, but notice not 4 is forced to be blue, yet connection not blue. Neighbor must be orange. Okay, with BFS, because it's not level by level going, we will start from 0, for example, from 0 node. And next we will color. We will color first 1. After 1 will be color, we will go to 2. We will color 2, and we will color 3. It's just how the DFS is working. If it will be BFS, we will first color 1 and 4. And then for example, for this level, we will try to color in another colors. So if we're thinking if we're going to solve with DFS, it will go with 1. We will color it in orange. Then we will color 2 in blue. Then we will color 3 in orange. Then we'll come to 4. But 4 connected with 0. After 4, we will go to 0. But 0 is already colored. And we will have a check in our DFS. I will show in code how we are going to check. And we will fail on this step. Is it clear? Okay. So this DFS, I will just show code, and then we will check the second condition. So using DFS, first we will color our node, like starting from 0. We will start to color it in blue. Then we take the nodes, the neighbors. So first neighbors will be 1. We will take neighbor, and we will check if neighbor is having already color, and if it's having the same color, like node 0 here. And if it is, then we will return false. But from 0 to 1, when we come, there will be empty color. So we're not going to fail there. Next, what we are doing, we're checking if neighbor color is 0. And it's this is check. And then we are doing DFS from our 1. And this condition we will fall down in this condition when we will be from 4 going to the neighbor 0. That's where we will return false, and we know that this graph is not actually biparated. This is clear, right? Okay. Now handling multiple components. So because graph could be when we're working with graph, it's not that we are having just one graph. So for example, it's usually from the input you just have this connection of adjacent nodes, but it could be that there is actually 2 graphs. This is one graph and this one another graph. And so we should keep in mind this case as well, that they are not connected. They are also not connected. And we have to run the phase for each of separate graphs. How we're doing this usually, we're taking graph, our adjacent graph, and we're, I believe, last time we also discussed, yes, right, with or not. This was the clone graph. This was the island graph. No, I believe we didn't discuss it. Okay. So how to handle when you have you're just going again in the your main function, you're working with for loop, and that's it. So basically, what will happen here? Here, for example, we will start. This is already output, right? It's colored output because we already colored them. But in the input, all of them will be 0. Also, regarding the coloring, how usually we coloring graphs? In the initial input, all of them will be 0. Having 1 second. I forgot somewhere. It should be mentioned how we usually coloring them. Okay, it's here. We need to ensure we color all components of the graph by calling the face on every uncolored graph. Just 1 second. There should be somewhere mentioned how we usually approaching coloring. We can realize what graph is impossible. No way to avoid the term. We potentially, for each node, we color blue color of neighbors, but notice must be blue, must be blue. This means the graph can be colored too, handling multiple colors. Somehow I miss it. Just in the implementation, we color not blue and orange using. So yeah, one step back. How we are coloring graphs. This is how we are coloring. We're creating just array. Array of the length of graph. Length of graph, it's how many nodes in the graph. So in this case, it will be 6 here. And this color array will be represented initially like this. What we're doing here, yeah, it will be 6. We will check. We will start from first node. We will check if the first node in the in our coloring is equal 0, means it's empty. Then we can go and run devise from here. Once we enter to devise, we actually for coloring using this one value, 1 or -1. It could be any. You could use, for example, whatever you like. For example, for 9, you can use 9, or you can use like 5, or you can create actually a color array in chars where you can define like a R, which stands for air, red, blue, yellow, whatever you want. You can actually use a string, so it doesn't matter how you're going to color. But the idea how we are coloring graphs is we're using array of the length of nodes in the graph. And initially, it should be something which is, that this graph is not yet colored. Once we're starting our devise from here, first color, we decided that it should be 1. We mark it here as 1. Next, we're taking, we're starting from this node, and will be 1 here. We check that our 1 here is actually 0. We start the phase. Here we're coloring. First things we're doing in our color array, we're doing coloring. Will be like this, and last will be left. So now from 0, because it's devise, it is and it is adjacent list, we are taking all his neighbors. In Java, it will be looks like this graph and neighbors. So basically, it will be 2 and 1 here. We're checking first, for example, it will be our 1. We're checking if 1 is equal the same color in our color array. It is not. At this step, it is 0. Our 1 is actually equal 0. Next, what we are doing, again, we're just checking if the, because what can happen. We also color array using for tracking if they visited or not visited already. If because this is like undirected graph, and at some point there could be that they not actually the same color, I mean, it could be that it is blue and yellow, but if it is yellow, it means we already saw it, this node, and we are not going to process and run the phase again. Otherwise, we will stack in the loop. So there is two things why we're using color array. First, for tracking visited arrays, visiting tracking nodes, and also for tracking the colors. Because our neighbors should not have the same color. Next, we will go and run the phase on 1. Here we will, and also notice, now when we second time calling the phase on the neighbor, we are actually calling with a different sign. So that's why it's very convenient to using 1 and -1. Because if you will using, for example, blue and red, like a string, you need to do the check. So, for example, you know this is one blue, and this then next we need to do red. But it is very easy. So next time when you're using the phase on your neighbor, you just sending color with opposite sign. And in this case, it will come here, and it will be our color array will looks like this. It will be 1, and it will be -1 here. Again, we will run the phase neighbors. In this case, the phase of neighbors will be, for 1, it will be 0, and it will be 3. Here, for example, we will check again our 0, which was colored. We're checking that the color of 0 is 1, and the current color is -1. They are not equal. We are not falling down here, but we know that this one has been already processed, and we will go and we'll start process the 3 nodes here. Is it clear? So it maybe sounds slightly complicated at the beginning, but coloring, it means only that you have array where you're tracking the 0, 1, or -1, and it is particular the visited nodes tracker. Yeah, I think I cover everything here. Do you have any questions? Yeah, just more practice, but guys, as you've seen from the last, that the tree and graph was very connected. And the most important about graph that you need just to learn what is DFS and BFS. DFS, it's recursion. Just be comfortable. Start from tree. Be comfortable with recursion on the DFS. Once you become comfortable with DFS, you're coming, and graph problem will be using the same approach like DFS. The one things which will be above, because for tree, it is direct graph, as we mentioned. That's why you don't need to track the visited nodes, because you are not going to visit the same nodes twice. But for graph, it's very important to using visited data structure or make modification in the matrix. And the one things, know the difference between when the graph is represented as a JSON list and when graph is represented with the matrix. When it is represented with matrix, you usually use this direction two-dimensional array to build just 2 graphs. So there is not that much to remember, but it is just once you will remember it. So yeah, and then practice, and everything will click. Okay, let's go to topological sort. Topological sort is quite advanced one topic, but I decided to include because I think we are good. On the 12 weeks, we are good to start with advanced topics. So, and it is very, very popular also. LeetCode task. So we have course schedule. Given an integer n representing the number of courses labeled from 0 to n minus 1, and array prerequisites. Determine if it's possible to finish all courses. Each prerequisite pair is represented as AB, indicated that course A must be taken before course B. Constraints. For any prerequisite A and B, A will not equal B. So in this case, meaning we are given a graph, direct one, because we have prerequisites. We can't, course 1 cannot be taken without first completing course 2 and vice versa. But in this case, we have cycle. So that's why we can't finish this graph. So we can't take all the courses because there is cycle when you need to finish 2 before taking 1, and also to finish 1 you need to finish 2. And in this case you need to finish first 0 course before taking 1. Is it clear from the description? Okay, so you're giving just prerequisites of the course, and because of courses depending on each other, we can build the undirected graph. In this case, by the way, this task is not giving as an input graph. So you're giving just two-dimensional array and the number of course. And this task probably, I would say, so for example, because for someone who has never practiced this kind of topic, you need to remember the pattern of this task. So for that, in this case, no one will tell that it is graph problem actually. So you will just click because you solved it before. That's why you know that this kind of task should be solved with graph. Okay, our goal is to check if enrollment into all courses is possible. Let's start by identifying which situation make enrollment impossible. Consider a simple case. So I covered it already in description, but there is cases where we can't finish course when one course is a prerequisite of another. This is means it is impossible to finish because it is a cycle graph. We're stuck in the cycle. Here also a couple of impossible enrollment. I believe this one is not right. This is like in our description example, also impossible, and these all three courses which depend on each other. Now I will start from the explaining algorithm. We will come naturally into understanding what is the topological sort. What do we notice about these cases in their graphical representation? They both have a circle relationship, a cycle. This highlights that it's impossible to enroll in all courses if there exists a circle dependency between courses. In other words, there must not be a cycle in the graphical representation of the course for complete enrollment to be possible. Another thing to note is that first course which can be completed are those without prerequisites in the graphical representation. Meaning, you can't complete a second course because in order to complete second course, you actually need to complete this one course first and then this one course first. This is something which is we will notice once we will build the graph. Let's call number of directed edges incoming to a node as in the degree of that node. without in the graphical representation. Okay. Let me simplify. So, for example, we have prerequisites of the courses. In order to take course 1, we need to finish 0 course. In order to take course 2, we need to finish 0 course as well. But in order to finish 2 course, we need to also finish the 3rd course. That's how we're building our graph. We will start. So, for example, we know there is a course with number 2, but in order to take it, we need to finish 3 and 0. And we build, for example, this part. But also we know that in order to finish 1, we need to finish 0 course. And we also build this way. And next, we know that for 4 course here, we have prerequisite, which is 1 and 2. That's how we are building our graph in here. Now, based on once we build our graph, so for example, what we can observe, in order to take 1 and 2 course, we need to finish first 0 and 3. So for example, I'm a student. I have a list of prerequisite course, which is I need to finish. And I need to build a strategy on how I have to finish all the courses. And I know there is some restrictions, which is stopping me for taking, for example, course 5. Because before taking course 5, I need to finish ABC course. That's how you're building the strategy. This is like to mapping to the real world. It's quite intuitive to find out that first you need to finish course, which is undependent on any prerequisite. And this one is actually just numbers, which is saying, so in order to finish this course, I don't need to take any other. It is 0, 1. But in order to finish this one course, I at least need to finish 1. Not at least, but I need to finish 1. In order to take this course, we need to finish 2 courses. For topological sort, in context of topological sorts, we're calling this in degree of that node. This the numbers. It's calling in degree, meaning how many relationships from how many these ages is actually in my node. In this, it's 1, and in this node, there is two connections, and it is 2. This is terminology, which is you need just to remember. This is a part of topological sort terminologies. And also, we discussed this in the in degree term in our previous lecture. It was somewhere here. Degree, the number of ages connected to the node. So this is clear, right? How we're ending up with graph. So it's directed graph. Now we know what is the in degree and why we are going to use it. I will explain. So have 0. Oops. Of my graph, my painting. How to clean this painting now? I will copy probably just the graph one. We'll color it green. So now that we discussed strategy, that we first will take courses or nodes which just have 0 degree. That's by pinking them. I'm saying that I took this course and I took this course. Once we took this course, what we need to do? We need to update degree of the next nodes. Because we took them, there is no anymore incoming ages to these nodes. It's become 0, and this one becomes 0 here. It is clear why it has become 0. If it's not, yeah. So basically, this is the graph, right? This is the initial representation of graph. we put in degree numbers here. In degree numbers, it is clear, right, from where this numbers is comes. Once we will start processing, we discuss why it is intuitive. We'll start processing nodes with 0 degree, because they're not depending on each other. We can start only processing these courses. On this means the pink means I deleted this. We process them. Once we process them, they are already not a part of our graph anymore. That's why we are also keep track of in degree, because there is no more incoming nodes to these nodes. That's why it's 0. It is 0, but this one still remains 2 because this nodes is here. And 5, it's having 1 because there is only one node, which is incoming to the 1. Now, now that we process these nodes, we are going to process these 1 nodes because they become 0. They are not depending. We are free to take these courses again. Now that we took these courses, we can update the next course with in degree 0. Means on next iteration, we can process our next node because it's within degree 0. This is one second. If like on this like stage, anyone is like click what we will how like potentially we will solve this task. I mean, this is reminds you like DFS or BFS it will go, and if it's so it I'm just asking how, for example, on this stage you will solve it. Will you use DFS or will you use BFS here? Because we're processing here level by level them, right? So it is should be BFS, right? And now, if you see, we are processing a couple of cores in parallel, meaning we should use multiple source BFS here. It is similar to orange infected task, because we will start processing from the multiple source. So, okay, was just see if you click. Okay. Let's now look at the example where it is impossible, how it will looks like. By the end of this process, no course remain indicates it possible to enroll. Now consider an example with cycling dependency. We have the same graph, but I added here dependency where 5. In order to take the second course, you need actually finish 5. So, and you can see there will be cycle dependency. Because in order to, yeah, you will see. So again, we will mark degree. We will remove this 1 nodes and this 1 nodes. Now we can't take 2, because in order to take 2, we need to take 5. But in order to take 5, you need to take 4. You can only take this 1 node. In this case, we took this node, but here we have cycling dependency. Whatever we will do, we can't finish any of this course because they are dependent on each other. It happens there are still unvisited courses. and cycling dependency exists, meaning enrollment is impossible. Now, how we will detect it? This basically our answer. We need what we need to answer in this task. If this graph has cycle dependency, if it has cycle dependency, there is no way for us to finish all the course, and we will return false. If there is no cycle, then it is true. How we usually detect if there is a cycle? Before knowing what is the topological sort, this task I was solving with the coloring of the graph. This with the algorithm from the previous where we were validating biparate graph, it's also can be solved this task, because biparate validation of biparate graph and coloring of the graph is also for detecting cycles in graph. In this case, you would be like coloring on the graph, and once there will be cycle, you will detect that with the colors, because you will eventually coloring your neighbor with the same color. This is like off topic, but once I learned topological sort, now this course schedule I usually solve only with topological sort. So now we detect cycle. So the whole idea of this task just to detect cycle, whether there is cycle or there is no cycle. Topological sort is helping to detect this cycle. How we're doing this? We tracked our nodes. We know how many courses we need to initially to take. Meaning, we will mark how many courses we took so far, which is actually the visited nodes. And at the end, we will check if we handled to visit all the nodes or we didn't. Because as an input, there will be a number of courses, which comes from the input. And we track how many visited nodes we had so far. And at the end, we will just to compare. If there will be cycle, because we can't process, we can't process courses within degree 1. We can process only courses with 0. Eventually, we will say that there is 3 courses which has not been finished. We will take a look at the code, and probably it will be more clear. So the whole process, which I just described with tracking in degree nodes, it is actually the topological sort algorithm. So the first sorting for vertical sorted and same way for every directed graph node comes algorithm design perform. Okay, let's see. And here, so the first step of the topological sort or CAN algorithm is determine the in degree of each course. This can be achieved by counting the number of times each course appear as dependent in the prerequisite pair. Course. So how we usually counting in degree? Now we want to process all the course. I will explain. So as an input, you have just 2-dimensional array with the prerequisite instructions, and you have number of course. You don't have graph here. So from the beginning of this description, you don't really know whether it is graph problem or it is not. Once you decided that it is graph problem, you need to build this graph. In all previous tasks, graph was given us. And in previous week, we were discussing that there is the way how we usually build graph. In this case, we will building graph which is not matrix one, but with a JSON list, which has this representation of map. Where integer it is node, and list it is our neighbors. Number of course is the number of nodes in this graph. So if there is 7 courses, it is meaning, so for example, there is 5. This is the number of course. It will come with 5 here. So this is number of nodes. That's why you're starting building graph. So you're putting first all nodes in the graph with empty array list with empty neighbors. Now you're taking all the prerequisite, because prerequisite is actually the things which is you will tell between which you have this edge, which is connecting one node to your neighbors. Who is actually your neighbors for your node? Because it is directed graph, as we discussed, we have strong relationship that we can't take this course before this course. It is our directed graph. In this case, we're building, we're taking graph, we're taking prerequisite 1, and it is our neighbors. Meaning here, there's also a bit something which is you need to notice. This our main node, it is 1, and it is directed with 0. So 1 is associated. 1 is the main node, and it has a list of, for example, in order to take course 1, you need to take course 0. Then you putting here 1, and you have incoming node, which is 0 here. Meanwhile, when you're building graph, you're adding, because it's topological sort, we introduce array with the number of nodes to track how many in degree coming here. So, for example, we had, I will copy it here. Oops. In degree, in this case, let me put the whole graph. So in degree, in this case, will be 0, 0, 0, 0, right? 1, 2, 3, 4, 5, 6. And here is 6. So initially, our in degree array will look this way. We are building graph. Once we will start from, we have prerequisite here. This our prerequisite cell. So what we're taking here, we are saying that our graph now with node 1 has neighbor which is 0 here. And here prerequisite 0. I think this one zero one, just number of course 1 and 0. There are a total of 2 courses to take. To take first course, you should finish course 1. So it's impossible. To take course 1, you should finish course 0. The LeetCode version is slightly different with the one which is we are discussing. So in order to finish 1, you need to finish first. Will be like this. And here, just 1 second, we will take 3 should be 0, which is 3 should be 1. Will be go in the degree. And this one in degree here will be 0 for 0, but it will be 1 for 1. And rest will remain the same for now. graph and neighbor 1. So which makes sense now. Is it clear, folks? Next, you will take 0 and 2, for example, here. And your 0 and 2, and this will be your neighbor, 1 and 2. And degree here will be 1. Next, you will have 3 and 2. You will have graph, which just has neighbor 3. And you will put here n, which is 2. And now you will update your n as a 2. I will remove this one. So that's how, from where we will receive this 2. So this part is understandable, how we're building graph and how we're building in degree. So basically, this is the initial step of topological sort. You need to build graph if it's not given, and you need to build in degree. Once you build in degree, do you remember we were discussing that first we will take those courses which is doesn't have any prerequisites. That's where we will build our multiple source queue. So we will check all in degree which is equal to 0. We will add them to the queue. We will track not visited. In this case, we track not visited, not just not at all because this is direct graph. We want, but it is with cycle, yes. But cycle in this case is will be solved differently. In this case, not visited, we just track in order to give answer whether we can possibly take all the courses or not. That's the main idea of not visited here, not to tracking whether this graph whether this node was visited before or not, where we are going to process it or not. Because how we are going to process? We're building a multiple source queue. We are adding 0. Once we process, we're just removing these connections at all. So in the queue, we put all initials in degree with the 0. We will start going with BFS. There is no modified BFS like tracking levels because we don't need to track these levels. We will take node. We will start process. We mark that yes, we can take this course. It is not visited, or you can call it like taking course, which is maybe makes sense in this context. Next, from this node, you will take what kind of neighbors means. Once you take this course, you're eligible to take these courses. You take all these neighbors here. You're keeping track in degree because you process this node already. You pop it out from the queue, means this in degree for the neighbors should be decreased because we're done with this course. That's how we are changing in degree here. And also you keep checking if the in degree n of this node is actually allowed us to take next course. And you keep adding in the queue if it is. Once you will reach to the point of here, of this graph, so imagine you process everything what is the possible so far, and you starting process neighbors, but because you're checking n degree n to 0, this only course which is eligible to take, means all this free won't never be a part of your queue here. And eventually at some point, this queue will be empty. But because we are tracking how many courses we took in this variable, it will be less than initial number of courses. And at the end, when you will giving your answer, you will compare not visited, how many courses you took actually, and how many courses was eventually actually as a part of input, and then you will say like it's true or false. So this is the whole idea of the topological sort. Topological sort using in degree. In degree array where it is tracking the incoming nodes, and it is process nodes from the if it's 0 or not 0, and you just how you're moving to the next one. Any questions, folks? So I created contest. I added for some reason C++ and C#. I was not adding sometimes in the week, but yeah, this week everything is fine, folks. Should be. Yeah, we have all the languages, and you will have 3 tasks. One is course schedule, the one which has been discussed. Another one to detect if graph is biparaid. So basically, this is the algorithm where we're coloring a graph in order to detect the cycle. This algorithm can be applicable for this course schedule, and I think I have even somewhere. Yes, so this is how I differently solve this with coloring them. And routing orange, yeah, this is kind of similar with topological sort when we're building multiple sources of PFS. So, yeah, any questions? Otherwise, congratulations, folks. We are on the last week. I'm very happy for you, folks. Yeah.
Lydia, thank you for the course today. I also wanted to know what are like, so this course schedule problem is new for me. Is there other ones that you know immediately that are similar to that one?
Yeah. This is the simple version of course scheduling with topological sort. There is a different variation of this course scheduling. And this course scheduling, the one which is we discussed, I would say actually it is the most simple one out of this one. Because usually on the topological sort, it is very advanced level. This one, which is very famous, and I remember like 5 years ago, I don't know if you folks remember, there is alien dictionary, which is Google very like ask. So it is hard question. It was always hard for me. But once you learn topological sort, you know how to solve this one task. So from the topological sort, course schedule is the most simple one, I would say. Maybe there is simpler, but I think it's most the simple, honestly. There is different variation of course scheduling, and topological sort, it is, as I mentioned, it is advanced topic, but it is very popular on the other side anyway. Yeah, so this one, I would say most top popular on the top. I don't really know who is more popular, Alien Dictionary or course scheduling, if I answer your question.
Yeah, it does. Thank you.
Yeah, sure. I'll send it. So then we can finish, folks, if no other questions. Yeah, and if some questions, we can speak on the Slack. Yeah, so have a good weekend, long weekend.
Thank
Thank you
you.
so much. I hope you learned something over these 12 weeks. It was quite a journey.
Thank you so much. It was very helpful session. I
Oh,
really
yeah.
appreciate it.
Don't take it personally, folks. It is advanced, but
Yeah.
we won't scale, right? Advanced topic as well. So
Thank you. Bye.
yeah, you're welcome. Bye,
Bye.
folks. Thank you. Thank you.